Okay, everyone, we ready to get started? Got a lot to do today. Okay, so last time we were talking about Lagrange multipliers. By the way, I posted a video yesterday on our YouTube channel going over that problem that we were doing in class where I gave up on the algebra. And I posted a video that showed that there actually is some algebra that can get us to the answer here, but we're going to do this problem at the end of class today anyway, so you'll see we'll have a better method for it. All right, so we were doing last time, where is it? We were doing this problem here where we were trying to find the max minimum values of this function of two variables constrained to this circle. And so the picture of this was a surface, which is the x squared plus 2y squared, and we were restricting it to this domain, x squared plus y squared is 1, and just plugging those points into the function, which gives us a curve on the surface, and we are trying to figure out where those highest and lowest points on that curve take place. And to do this, we implemented the method of Lagrange, which is to find all values of x, y, and lambda such that the gradient of f is equal to lambda, which is just a number, times the gradient of g. So basically, we're trying to figure out what x's and y's and lambdas make it so that the gradient vector of f is equal to a scalar multiple of the gradient vector of g. In other words, where these two vectors are parallel is what we're trying to determine. And then we also have to satisfy this equation, which is actually the constraint equation. And if we can find the x, y, and lambda that do that, then the largest value we get out would be our max and the smallest would be the minimum. So we started doing this. We didn't finish it. We took the gradient of f, which was this, the gradient of g, which is treating that left side of this equation like a function, taking its gradient. And then we went ahead and set the gradients equal to one another, or sorry, the gradient of f equal to lambda times the gradient of g. And it broke down to be 3 equations. And we were going about trying to solve these equations. I said they're non-linear equations, so we can't use matrices. And so what we did is we started with the first one. We divided by 2, we moved everything to one side. We got 2 solutions, x is 0 and lambda is 1. We did the same thing here, and we got y is 0 and lambda is 2. And so we started by saying, all right, let's let x be 0. So we're looking at like this case right here. And when x was 0 and we let y be 0, okay, we would satisfy both of these equations, but this third equation would not be satisfied. So basically that told us we can't have that happen. And then we said, all right, well, let's try x being 0 and let's let lambda be 2, which would satisfy the first and second equations. When we did that, let x be 0 and lambda be 2, we plugged 0 into the third equation and we got 1 and -1 for y. And so now we need to continue. All right, so to continue, I'm going to try a different scenario. I'm going to let y be 0 here. And then that'll make the second equation true. But over here, again, I can't let x be 0 because then we'll have the same problem we ran into on this case. So I have to let lambda be 1. If we do that, then the first equation and the second equation are true. And so now I just need to go figure out what would happen with the third equation if I let y be 0. So in equation 3, if y is 0, we get x squared must equal 1, which means x must be plus or minus 1. So that means that x could be 1, y has to be 0, or x could be -1 and y would be 0. And in both of these cases, lambda is 1. So it looks like we have 4 potential points here where we have either maximums or minimums happening. Now, how do we determine now what's going to give us the max and the min? What do y'all think?
The lambda?
Lambda's, well, lambda tells us what the scalar multiple is, but how do I know whether or not 1, 0, -1, 0, or 0, 1, 0, -1 gives me a maximum or minimum on that curve?
Plug it in.
Plug it into the original function, right? Into this thing right here. We want to plug it into that. So I'm going to just bring that down here and we'll just start plugging in. So now I'm checking. Okay, so this is my checking step. I'm trying to squeeze it all onto one page here. I'm going to check all 4 points. So let's try the point 0, 0. I'm sorry, 0, 1. If I plug 0 in for X, 1 in for Y into this, so I'm checking this first point right here, then I get 2. If I plug in 0 for X and -1 for Y, I also get 2. If I plug in 1 for X and 0 for Y, that's this point here, then I get just 1. And if I plug in -1 for X and 0 for Y, I get 1 also. Does that make sense, everyone? So our maximum value, right? Our maximum value is 2, and it actually occurs at 2 different points. And our minimum value will be 1, and it happens at 2 points. And if we go back and check the actual picture I showed you, you can see that we do have 2 maxes and 2 mins. And to determine where they are, we probably have to look from the top like this. And I believe my axes, this is my x-axis right here. This is my y. So it looks like at 1, 0, and then this is 0, 1, and then this is -1, 0, and this is 0, -1 down here. So you can see that if I turn that, we have 2 for these 2 points and then 1 for those 2. Does that make sense? It's a lot of messing with the equations, trying to figure out what scenarios make all of your conditions be met. So let's try another problem. Okay, we're trying to find the maximum minimum values of this on this disk. Okay, you know what? I'm not going to do that. Here we go. So look at the previous problem. We were trying to find the maximum minimum values of this function on this circle. See how this is x squared plus y squared equals 1? And so we had the circle on the ground. On the next problem, we want to find the maximum values of the same function. It's the same function, but now on this disk, x squared plus y squared is less than or equal to 1. And so that means my domain is not just the circle, but it's an entire disk down here. And if we plug every point in that disk into the surface, we get this green surface. And we're trying to find the highest and lowest points on that green surface. And so let me take the domain out of here. I'll take the original surface completely out. We're trying to find the highest and lowest points of that whole thing. And you can see we have 2 high points. And then we also, our lowest point is actually down here now. Do y'all see that? See, it's down on the bottom. These 2 points, are not our lowest points anymore because we're including the whole surface. So the difference between this problem and the previous one is the inequality sign. All right. And Lagrange does not deal with this scenario. Okay. Lagrange does not deal with this scenario. Lagrange only deals with when you have strict equality here. And so it can tell you what's happening on the boundary, but it tells you nothing about what's happening inside. So to figure out what's happening inside, we're going to do something we've done before, and that is we're just going to do kind of what we did to calculate capital D. We're going to find the critical points.
I have a quick question.
Good, yeah.
Oh, I just wanted to ask, how did you get that green again? Because you were talking about the domain of the disk.
Yeah, okay. So
what does the green represent again?
okay, let me go back to this one.
Sorry.
So let me back things up. Okay, so if I have this surface, right? This surface is created by taking every point on the XY plane and plugging it into this function, and it draws this surface. That's this orangish color. But if I tell you you're supposed to restrict it so the only points you can plug in have to live on this line, then that means the domain, the only things you're allowed to plug in are points on this line. And so if I take a point, like let's say here, we plug it into the function, it's going to spit out a number. It's going to be somewhere here, right? Take another one, it's going to spit out some number here. If we put all those together, it will draw yeah, my picture wasn't perfect, but it goes up here like that, right? So you get just the blue curve.
Okay.
And we're
Yeah.
saying, this question is asking, if you look at the blue curve on top here, what was the highest and lowest points? And so we use Lagrange. For this problem, our domain is no longer restricted to a circle, it's restricted to a disk. So that means it can be not only all the points along the edge of this circle, but every point in the red region. Does that make sense? And so when I start plugging all of those points in, not only will I get that blue curve that we had before, we'll get all the other points. And that's where you get this green piece from. Does that make sense?
Yes, thank you for explaining it.
Good. No, please ask questions. All right. So we already know the max and min values of this thing along the edge, right? We just did that work. Okay, so we're not going to have to redo that work. We already know that if you go along the edge, we used Lagrange to find that point, that point, that point, and that point, right? We did that in the previous example. So all we're going to do is make a slight adaptation to this problem, and we're going to find the critical points, which means we need to find out where the partial of f with respect to x is 0 and partial with respect to y is 0. If we can figure out where these two happen, then we have a potential place where we have a local max or local min. So this goes back to 11.7 is what we're doing in the previous section. So that's all I'm going to do. I'm going to take this. So I'm just going to state here on x squared plus y squared equals 1, we know that when you plug in 1, 0, it spits out 1. When you plug in -1, 0, it spits out 1. When you plug in 0, 1, it spits out 2. And when you plug in 0, -1, it spits out 2 also, right? That's what we did in the previous example. So now what we do is we say, all right, well, let's take the partial of f with respect to x. Okay, that's just 2x. Let's take the partial of f with respect to y. That's just going to be 4y. And let's set both of those equal to 0. And these are easy solutions, right? X must be 0, y must be 0. And so the only point that could possibly satisfy both of those at the same time would be the point 0, 0. So now this is the new thing we need to look at. What happens at 0, 0? Plug that into the original function and you get 0. And now is our min, right? That's our min. This still is the max. We still have a max of 2, but now our minimum value is 0 and it happens at 0, 0. So that's why I go back and look at this picture and I look at the green, right? And I'm looking for the max and mins. Take the domain out of here. We still have these two. This is still our max points, but our min now is down there on the bottom at 0, 0. Okay. All right, so let's go to the next one. I'll show you the picture after we do the work. I'm also going to go grab, oh, you know what? I need to be doing today's notes. Let me do this. Okay, here we go. I wanted to also grab the Lagrange steps. Where are they? Here we go. Or the formula for Lagrange, what we do. Okay, so dang it. Here we go. Okay, so what tells us we can use Lagrange here? Well, we're trying to find the max and min, right, of a function of two variables that has a constraint equation, right? That's what makes you know you're going to use Lagrange. A function of two variables constrained to some equation. Once we establish we're using Lagrange, the left side of this equation is our g of xy. And so what we need to do is find all the values of x, y, lambda such that this is true and this is true. All right, so this condition right here, that the gradient of f must be equal to lambda times the gradient of g, really means that the partial of f with respect to x, partial of f with respect to y, that vector must be equal to lambda times the partial of g with respect to x, lambda partial of g with respect to y. So I just took the gradient of g, which is just partial of g with respect to x and then y, and then multiplied it by lambda. Does that make sense that this right here is what this means? And then every time we do a problem like this, we're going to set this equal to that. We're going to set those equal, and then we're going to set this equal to that. So we will wind up, for all these problems, we will wind up having three equations each time that we have to satisfy. The first equation we are going to have is going to be the partial of f with respect to x must be lambda partial of g with respect to x. The second equation we're going to have is the partial of f with respect to y must equal lambda partial of g with respect to y. And the third equation we have will always be the constraint equation, this right here. Every problem that you do using Lagrange, where you have a function of two variables and a constraint equation, will require that you solve these three equations simultaneously. So let's do that first one. Okay, for this problem, the partial of f with respect to x is just 4. That must equal lambda times the partial of g with respect to x. Well, here's g, right? So the partial of that with respect to x is just 2x. The second thing I have to have is that the partial of f with respect to y, which is 6, must be equal to lambda times the partial of g with respect to y, which is 2y. And the third equation is the constraint equation, which is x squared plus y squared must be 13. Any questions? All right, let's see if we can't figure out how to do this. Any ideas? Any ideas on the algebra here to figure this out?
For 1 or 2, we would solve for lambda first.
We
Shot in
could,
the dark.
we could take both equation 1 and 2 and solve them both for lambda. If we do that, then we could set them equal to one another, couldn't we? Okay, that's worth a shot. Okay, so let's do this. Let's solve the first one for lambda. How would you get lambda here by itself? What would you do?
Divide by 2x.
Divide by 2x, right? Now, you have to be very careful here. Because if you divide by 2x, you have to promise me that x will never be what?
0.
0. I need to state that. If x is not 0, right, then what I can say is that lambda would be equal to 4 over 2x, which would be just 2 over x. Okay, I'm just trying to work this first one right now. Do you understand the importance of me saying x can't be 0 here? You can't divide by a variable if you don't have control over it. So I'm controlling the x. I'm saying, okay, lambda is defined to be 2 over x so long as x isn't 0. Now, similarly, what can you say about this one? If y isn't 0, right, then you could divide both sides by 2y, and what would you get? Lambda is 3 over y. You agree?
Now, if you would have solved for lambda instead, you would have to do the same thing, or solve for x.
Solve for x in terms, yeah, and then divide both sides by like 2 lambda.
Yeah. So
Yeah,
would
then you
you
would have
say
had to
that
have
lambda?
said, you would have to
Okay.
say lambda can't be 0, right?
Okay,
So you'd say if lambda is not 0. So we can do that. I mean, it can be like a separate thought within the same line. We could have said this, if lambda is not 0, then we could say x is equal to 2 over lambda, right? That's just taking that equation, solving it for x, dividing both sides of this by 2 lambda. And over here, we could have done the same thing. If lambda is not 0, then we could say that y would be 3 over lambda. Y'all with me?
I have a question.
Yes.
So to solve for these three equations and to make it work, we're restricting our domain of x and y to not include 0. But our original function that we're searching for the maximums of f of x and y does include 0 in the domain. Does that mean later on at some point, we're gonna have to check 0, 0 to make sure that we're not overlooking anything?
Yes and no. This definitely does not have a domain restriction of 0. We are allowed to plug in 0, 0, right?
Hmm.
But if we're constrained to this, we can't use 0, 0,
Oh,
right?
that's true.
But you could let x be 0 and not y, right?
Okay.
Or you could let y be 0 and not x. We're gonna have to
So-
look at all these scenarios.
Okay, that was essentially my question.
Yeah. Okay, so which way do y'all want to go? Okay, let's start with where we started with, or with what we started with. We started with saying, hey, can we solve this for lambda? We did, we solved it for lambda. We solved this one for lambda. Let's stick with the black ink here. If I have this and this, right? Then what I'm saying is if x is not equal to 0 and y is not equal to 0, right? If they're both not equal to 0, then I can say that lambda was 2 over x, but also lambda is 3 over y. So I could say 2x is equal to 3 over y. Y'all agree with that? Okay, now if that's true, now I have a relationship between x and y. In fact, I could say, like cross multiply kind of, I could say 2y is equal to 3x. And I don't know, just for heck of it, I'm gonna solve for y. So y is 3/2 x. Do you agree? So in this case right now that I'm looking at, if x isn't 0, y isn't 0, I have this relationship. And what about this? I need the third equation to be satisfied. So if I look at equation 3 now, it's going to be x squared, right? Plus y squared must be 13. But what did I just say the relationship between x and y was? This, right? So I could rewrite that as x squared plus 3/2 x squared must be 13. And hey, look, now I have an equation with one variable in it. And I can solve for x. If I were doing this, I'd probably clear the fractions out by multiplying both sides by 4, or 52. And then I get 13x squared equals 52. So x squared is 52 over 13. And x equals plus or minus the square root of 52 over 13. All right. That makes sense? So here's where we are. I know that x could be root 52 over 13, or x could be negative root 52 over 13. Okay, what would the y have to be? Well, y is going to have to be 3/2 x, right? Y is going to have to be 3/2 x. So why don't I just take 3/2 and multiply it times that square root?
Isn't the square root of 52 over 13 just 4?
Yeah, what is that? That number?
Isn't it 2?
Is it?
Because 52 divided by 13 is 4.
It's 4, yeah, okay, those numbers are gonna be nicer. I wasn't even paying attention to that, actually. Yeah, everyone, 52 over 13 is 4, so both of these are all just square roots of 4, which are 2, so let me just rewrite those. This is 2 and then 3, because if that becomes a 4, square root of 4 is 2, 2's cancel, you just get 3, and then the other one is -2, and then what, -3? Okay, so let's just kind of think about this for a second. We have X and we have Y, right? We have another X and another Y, where we could potentially have a max or min. We know that this X and this Y satisfies the third equation. We know that this X and this Y satisfy this relationship that must be held to have the first and second equations hold true. My only kind of other question would be, like, what would lambda be for these? So like here for this one, what's lambda have to be? If Y is 3 and X is 2, then what's lambda? So you can get it from right here. If you just like replace this Y right here with 3, then what would lambda have to be?
1.
1. And then now if we do this point, let Y be -3, excuse me, lambda would have to be -1. Now the lambdas don't actually, they're not part of the answer in terms of, you don't need them to find the max and min, but for each point X and Y that you find, there needs to be a lambda that corresponds to those. So we have found the X, the Y, and the lambda where we might have a max or min. We found another X, another Y, and another lambda where we might have a max or min. Okay. We're not done though. And this is what I think makes Lagrange so difficult. We're not done because we have to exhaust all the possibilities. Our conditions here were that X and Y couldn't be 0, right? So now let's actually think about what if X was 0, right? Okay, so let me consider this. I'm going to do a different color. I'm trying to do this all on the same page. Okay, so let X be 0. Let's start with that. Okay, what's wrong with that? If X is 0, what's wrong? Can I let X be 0?
Equation 1.
Equation 1 won't hold. Look at equation 1. Equation 1 then becomes 4 equals lambda times 2 times 0, right? And that means that 4 is equal to 0, which isn't true. So I can't let X be 0 or else equation 1 isn't going to be true, right? Similarly, if I let Y be 0, we're going to run the same problem, aren't we? But with equation 2 this time. Equation 2 will give us that 6 equals 0, and that's not true. Understand? So this said, look, as long as X is not 0 and Y is not 0, here's what we're going to get. But we had to then consider, what if one of them is 0? Well, if X is 0, you can't hold equation 1 to be true. If Y is 0, you can't hold equation 2 to be true. So you must have that both X and Y are not 0. And therefore we're done. Do y'all see we've covered every case? Okay, so now which is the max and which is the min? So we have to actually take the original function here, and we need to plug into those two values. So we plug in 2, 3, and we plug in -2, -3. We plug in 2, 3. Let's see, we get 8 plus 18, so we get 26. And if we plug in -2, -3, we get -26. This is our max, and this is our min. Questions?
I'm still confused by what lambda tells us.
Lambda doesn't tell us anything in terms of our final answer. It's the Lagrange, the whole idea behind Lagrange is that you will have maximums or minimums anywhere that the gradients of these two functions are parallel, which means that they must be scalar multiples of one another. And therefore the scalar multiple is something that you would be able to determine. And so the X and the Y, right? The X and the Y are two things that are going to be important for us to calculate the max and min, or determine if it's a max or min. But the lambda is always just going to be that scalar multiple, that number that the gradient vectors are multiples of one another, right? It's that scalar multiple. It's not relevant to the actual like calculation of what the max and min is. Let me show you something. I was going to wait till maybe after another example. Let me do this. Let's first look at this problem we just did. Let's look at what we just did. We started out with f of xy equals 4x plus 6y. By the way, that's a plane. So we have a plane. And we're going to restrict that plane to this, which is a circle, right? Everyone, that's a circle. So if I just make the domain, that stuff on the ground. Okay, so Fabiola, I hope that that makes sense. Again, we're going to just take just those points on the XY plane, plug them into the plane. If we do that, we get that curve, the blue curve that's at an angle. And we were trying to find the highest and lowest points, and there they were. We had a highest point, it was what, 26 or something like that, and this is the lowest point, negative 26. And we found out where they happened, right? It was, one of them was at 2, 3. So if I look from the top, if you go out x2 and y3 comes straight up at us, we'll be up at 26. If you go -2 on the x and -3 on the y, it will take you down to negative 26. Yay or nay?
That works for me. Someone asked a interesting question in the chat, by the way.
Oh, yeah, I've been avoiding the chat because when my computer crashed last time, it was when I was in the chat, so I'm afraid to open it, but I will. Oh, okay, so we start talking about eigenvalues. Okay, yeah, that's a little outside this class, but yes, you can consider an eigenvalue. I would guess that most people in here don't know what eigenvalues are, though.
No.
Yeah,
Heard that
maybe
word.
maybe that's another video I make and just send out to everybody, like on my own time, and I'll just send it out.
Sounds good.
Yeah, I took linear algebra before this, so that was like
Yeah.
the last thing we covered.
Yeah, yeah. In some sense, you can consider it an eigenvalue. It's, yeah, okay, I'm not going to get into it. Okay, so I want to show you, look, Daniel, I want to answer your previous question about like what's the value of lambda and stuff. I think I want to try and show you all the Lagrange method, like a visual proof of why it is it works. Okay, this is a visualization of Lagrange's method. So I wrote this code a couple of years ago. So here's this is always very difficult to explain, but I'll try. Remember, Lagrange says that if we can find an x, a y, and a lambda where the gradient vectors of f and the constraint g are parallel, right? That's where we have maxes and mins. So right now, what we're looking at, okay, right, this thing that we're looking at right now is the constraint function. Okay, so remember how in the Lagrange we said we're going to have a g of xy equals k. And in the previous problem that we just did, it was x plus y squared equals 13, right? If we look at just this part as a function, that's a surface. And we're saying, when is this surface equal to 13, right? That's what this equation means. So if I just look at g of xy, let's just say that this is it right here. It's just some surface, okay? Now, that right there is that surface restricted to 13, let's say, okay? So this is actually the green is where that surface is a constant. So you should have like a horizontal line or a plane cutting through your surface. So there is the actual constraint equation. Now here's what the gradient looks like. So remember, the gradient is a vector. So at every point on this green curve, we have a gradient vector that sticks out. Remember, the gradient vector is the direction. And so this goes back to what we learned before. The gradient vector always points in the direction of maximum rate of change. Remember when we were trying to do that with the directional derivative? And we said, oh, with a directional derivative, you can point in any direction. So the question ultimately became, what direction do you point in order to go with a maximum rate of change? And it turned out that it was the same direction as the gradient vector. So this vector right here tells us that if we start going out this way, okay, let's do it. We start going out this way, this direction, we're going to be moving up the surface, and that'll be the steepest rate of change. So there's our green gradient vector. So now I want to show you that circle right here. I want to show it to you projected down to the XY plane. And now I'm going to show you that gradient vector just superimpose, or like the shadow of it straight down. Okay, y'all got that? This gradient vector right here is the gradient of G, which is on this surface pointing in this direction. I'm going to take all that other stuff away. Okay, so everyone understand what that represents down there? You know what, I'll put that circle back down there on the ground. Okay, that's the constraint information. Now, we're trying to find the max or min of another surface, right? F of xy. Well, here's f of xy, it's a different surface. I know it may look the same, but it's not. Y'all see those are different? Okay, so this is a different surface. This is f of xy. And so let's look at what f looks like restricted to this constraint domain. That's that curve up here. You see that? Now, let's look at the gradient on the blue curve. See the gradient on the blue curve? Yes? Yeah?
Yes.
Okay. Now, are these two vectors parallel? Let's see. Let's look at them from the top. Do they look parallel?
No, but almost.
Almost, right? So what I'm going to start doing is I'm going to start moving a point around. You ready? Here it goes. Watch what happens to the gradient vector. Might be zoomed in too much here. You know what? It's hard to see it here, isn't it? It's hard to see it here. There's a blue vector here and green. So I've got something here down here for you. This is a top view of the two vectors. It's easier to see them this way. So I'm going to back it out a little bit. When we were over here, if you look from the top, this is what it looks like. Do you see that they are not parallel? Look what happens though when you get to the highest point on this curve. I may have passed it right there. When I get to the highest point on this curve, look at the gradient vectors. They're parallel. And that's not a coincidence. That is Lagrange's method. Lagrange is saying if you want to find the highest point on a curve, you just need to figure out where this gradient vector is parallel, a scalar multiple of this gradient vector. Let me back it out. Let me go to the lowest point over here. See, now I'm at a lowest point, and look what happened to the vectors. They're parallel again. If you go anywhere else, they won't be parallel. Now, this is not a formal proof. This is just a visual confirmation of what Lagrange is telling us we can do. So that's why the lambda doesn't really matter. The lambda is just some scalar multiple, all right? Some number that shows that these vectors are parallel to one another. What's important to us is the x and y where it occurs. But for every x and y where it occurs, we should have a lambda. I hope that makes sense.
That makes a lot of sense, but I'm interested to know why they line up and become parallel at max and minimum values.
Yeah, so that's a more like the formal proof is what you're talking about.
Yes.
Like that's a, you know, there's just some things in calculus that we have to take on faith until you become a math major, and then you go back and you basically prove all the theorems from calculus. I mean, that's what math majors do. We go back, we start from the very beginning, we start proving all the theorems. And so Lagrange is something that you may study if you're a math major. and you actually go through and have a formal proof of this. This is just a visual confirmation, but I hope it at least shows you a little bit of what we're trying to do, right? Okay, let's go to the next example. All right, same thing. We have a function of two variables, x, y, f of x, y. We have a constraint. This time it's not a circle, is it? But it is a constraint equation. So this is our g of x, y. And so because we have a function of two variables and a constraint equation, I know that there are three things that I have to look at. Partial of f with respect to x equals lambda partial of g with respect to x. Second thing I need to make sure is true is that the partial with respect to y is equal to lambda times partial g with respect to y. Third thing I have to make sure is true is that the constraint equation is satisfied. Every time, those are my three equations. Now, the first equation, let's do this. The derivative of f with respect to x should be y e to the xy equals lambda. Now, partial of g with respect to x would be 3x squared. I hope everyone's comfortable with y e to the xy as being the derivative of e to the xy. Derivative with respect to x, I should say. Any questions there? The next one is x e to the xy equals lambda partial g with respect to the y is 3y squared. And then the last one is the actual constraint equation, which is x cubed plus y cubed must be 16. Oh boy. Okay, well, what do we do? I mean, we could solve for lambda again, couldn't we, and set them both equal to one another? And we could do that. I mean, this is where really like the algebra is just up to you, and you've just got to make sure that you're thinking through all the possibilities and not leaving anything out. I think that's what makes it hard. I know that's what it makes it hard to grade, because I have to make sure that you've considered all possibilities and that you told me you considered all possibilities, right? You can't just do the ones that work and then never have said, oh, look at this. Oh, but I can't do that because of this. You know what I'm saying? Like on this right here. Like when I did this, this has to be in your work. Like I have to know that you did consider that, because here you didn't. You said, no, I'm not going to let x and y be 0, but then you have to at least address what if they were. All right, so how in the world? So I'm going to show you, this isn't a trick, but it's something that comes up sometimes that you can do this on. Do y'all see that this and this are almost the same? Like they're almost the same. One has an x, one has a y, right? So here's what I'm going to do. Okay, if, just hear me out first. If x is not equal to 0 and y is not equal to 0, then the following is true. X, y, e to the xy equals lambda times 3x cubed, and x, y, e to the xy equals lambda times 3y cubed. Okay, what did I do there? So x is not 0 and y is not 0. And then I have this.
Multiplied by x and y.
I took the first equation right here and I multiplied it by x over here and over here. And that created this equation. Now I had to say x can't be 0, right? Because if you multiply both sides of an equation by 0, then of course it's going to be true, right? So I have to say, no, x can't be 0 here. And then where did this one come from?
Multiplying both sides by y.
This equation though, right?
Yeah.
So this is like, this was equation 1, but I hit both sides with an x. This is equation 2, but I hit both sides with y. Now, why did I do that?
Set them equal to.
Yeah. These are now both the same, aren't they? xy e to the xy and xy e to the xy. So now I can set this and this equal to one another. So it's just a little, it's just kind of a clever little trick. That should be x cubed. I'm going to bring everything over to one side. Okay. And then I'm going to factor. I can pull out a 3 lambda. I'm left with x cubed minus y cubed equals 0. Why did I factor out a lambda instead of at this step just dividing both sides by lambda?
Because we need a lambda at the end, because they're vectors.
Yeah, but if I divide by
Lambda
lambda,
can't-
then I have to say lambda can't be 0, right? And then I've created for myself another thing I have to think about, like, oh, but wait, this is when lambda is not 0, so I'm gonna have to go back and think about what if lambda was 0. And so I just decided to factor over, or move everything over and factor, because it's just kind of a safer way to go about things algebraically. Now from this, I get 2 solutions, lambda is 0 or x is y. So that's just because, you know, I set 3 lambda equal to 0, I get lambda 0. Then if I set x cubed minus y cubed equal to 0, that gives you x cubed equals y cubed. Then you take the cube root on both sides and you get x must be y. Y'all agree? Okay, all right, where the hell are we? I'm lost. All right, so let's do these one at a time. Remember, we're working all within this construct right here. We're assumed that x and y were both not 0, and what we've determined at the end is that either lambda is 0 or it's possible that x must be y. I'm going to go with the x equals y first, okay? So I kind of had 2 different scenarios now. If x equals y, then what can I work with now? I know if x is y, that this is true, right? So I've satisfied these equations. But what equation have I not satisfied?
Third one.
The third
The
equation.
third one.
Third one, right? So if x equals y, then equation 3 becomes x cubed plus, well, wait a minute, y is x, right? So x cubed again equals 16. And that means that 2x cubed is 16, which means x cubed is 8, which means x is 2. Right? Now, if x is 2, what's y? 2 also, right? Because x is y here. So if we determine that x is 2, then y has to be 2. So it looks like we got something promising here. We got 2, right? And then lambda, what would lambda be in this case? For 2, 2, where's lambda? Shoot, do I even know anywhere where lambda would be? If both x and y were 2? Well, couldn't I come up here and figure out what lambda is? Just grab one of these. Just plug in 2 for x and 2 for y. Right, see? And then this would be 2e to the 4th equals, let's see, 4 times 3 is 12 lambda. And then divide both sides by 12. So I get something like e to the 4th over 6. I'm just showing again that we found an x, a y, and a lambda that satisfy Lagrange's requirements. We're not going to need the e to the 4th over 6. We're not going to need it for anything. But that is the scalar multiple. That is the lambda that makes the 2 gradients parallel. Okay. Am I done?
You have to test if x and y are.
Yeah, so this was saying x wasn't 0 and y wasn't 0, right? That's what that was saying. Now, before I get to that, didn't we still need to look at what happens when lambda is 0? right? Look at that. So what if lambda is 0? So if lambda is 0, let's go back up and look at equation 1. What would that tell you? What would equation 1 tell you? Equation 1 would say that y e to the xy must be equal to what? If lambda is 0.
0.
0. And the only way that y times e to anything would be 0 is if what was 0?
Y.
Y. So that would mean that y must be 0.
But we already assumed y can't be 0, correct?
Yeah, but we said y couldn't be 0. So this is a contradiction, which means lambda can't be 0. Understand? So I would say this is the symbol we use for contradiction. Have you all ever seen that? Do you all know what that is?
Nope.
Okay, have you seen, I just used this right here. Did you see that right there, that arrow? That was like x equals 2, but that implies that y must be 2 because of this relationship. What you see here is actually 2 arrows pointing to each other. And so it's a contradiction. It's like saying, it's like you have 2 things pointing in opposite directions towards one another, right? Opposite, not opposite direction, in the same, like it's a contradiction. They're hitting each other. So this is no good. Y cannot be 0. And then if I said that y couldn't be 0. So we can eliminate this possibility. So I would say we are done with this kind of mental construct that we just went through, we're done with. If x and y are both not 0, then this is our conclusion. 2, 2 with lambda being e to the 4th over 6. But now I need to go and look at the other cases, right? So let me look at the next scenario here. If x equals 0, okay, let's see, are we going to run into any problems? Look at the first equation. Just look at equation 1. If x is 0, then equation 1 becomes what? Y e to the 0 must equal 0, right? If x is 0. But what would that mean?
It means y is 0.
That means y is 0, right? So if we're going to let x be 0, then that forces y to have to be 0. But what's wrong with that? But then
We already figured out that y can't be 0, right?
over here, okay, so this is a different, you have to remember, this is a
Okay, yeah.
completely different idea. So we've put this one to bed, right? And now we have like a brand new kind of idea.
It doesn't
If x
satisfy
is
the
0,
third.
y would have to be 0 to satisfy equation 1, but then equation 3 would turn into what? 0 plus 0 equals 16, right? Which isn't true. That means I can't let x be 0. If x is 0, it forces y to be 0, and once you have that, equation 3 will never be withheld, will never be upheld. So that can't work. One more thing to think about. What if y is 0? Well, if y is 0, look at this equation right here, equation 2. What would equation 2 tell you? That x e to the 0 must equal 0, right? If y is 0 there. And that would mean that x is 0, right? But equation 3 would then say that 0 is 16, which is not true. So are we done? We've looked at it all, right? We've taken the scenario where both x and y aren't 0, and we came up with some number, right? Or some point. And then we looked at when one of them wasn't 0, or sorry, when one of them was 0, and it forced the other one to be 0, which made equation 3 not work. And it did it both ways if we did x is 0 or y is 0. And of course, we don't look at when they're both 0, right? Because if they're both 0, obviously equation 3 is not going to be upheld. So we're done. But wait a minute, isn't this supposed to give us max and min? Isn't it supposed to give us max and min? We only have one answer. which means that we either have a max and no min, or we have a min and no max. So let's take this value and plug it into the original function. Here's the original function. Okay, let's plug this in. F of 2, 2 is e to the 4th. How do I know if that's a max or a min? So 2, 2, remember 2, 2 satisfies this equation, right? 2 cubed plus 2 cubed, that's 8 plus 8 is 16. And when we plug that in, we're getting e to the 4th. I don't know if that's the highest point or lowest point. So to check it, all we have to do is compare it to any other point that satisfies this constraint. So how about cube root of 16, 0? Do you all agree that that point is in here? Yes? So what happens if I take the cube root of 16 and cube it? I get 16 and then 0 here. So that would satisfy that equation. But now plug that into this and see what we get. We get e to the what?
0.
0, which is 1.
1.
So look, do y'all see that 1 is smaller than this? That means this is a max and there is no minimum. The reason it's the max is because if I can find one point and see what the answer is, if this is bigger than that, then that's got to be the maximum. There should be no other point that's bigger than this, right? If this is not the maximum, then that means that there should be some other point bigger, right? Does that make sense? If this is smaller than that, then you know it's a max. If this was bigger, let's say this turned out to be like e to the 10th, then I would know that's a minimum. Y'all ready to look at it? Let's look at this thing. Okay, so here's the function, pretty cool. F of x equals e to the xy. And I constrain it, so the domain, here's the domain looking from the top, but I'll draw it here. There's the domain. So I'm only plugging points into that surface that are on that curve. So here's the curve. Can you all see it there? Let me pull the original surface out. That black curve is the surface constrained to that equation. And I hope you can see from that that we only have a highest point right there. And that it drops down on both sides and it goes down like asymptotically approaching 0. So you don't have a minimum because it's asymptotic, right? If you have something that's approaching 0, it never gets there. It would never have a minimum value. You could say it has a lower bound, the number never goes past, but you couldn't say it has the smallest value. What do y'all think? Yeah. Let me see, we have this one. Let me see if there's another one after. Yeah, let's see if we can crank this one out real quick. Are you all understanding the kind of the logic that you have to run through? This is an important topic, especially for like computer science or math majors, is you have to know that you've exhausted all possibilities. You have to know that you've looked at all the different scenarios. You can't miss anything. All right, so here we go. We've got a function. We've got a constraint. It's a function of 2 variables, x and y. Here's our constraint. That means I'm going to need 3 equations. First one is partial of f with respect to x must be lambda, partial of g with respect to x. Second equation, partial of f with respect to y must equal lambda, partial of g with respect to y. Third equation is g of x, y must be k. Okay, what is the partial of f with respect to x? Why don't I give you all a moment to see if you can figure out, just set these equations up, see if y'all can set them up. I'll give you 3 minutes. Okay, hopefully you got that. I think it's easiest if you do this problem just looking at 1 over x as being x to the -1, and then 1 over y as being y to the -1, and then same thing here, x to the -2, y to the -2. And then when you take the derivatives, you just do chain rule, right? Any questions on that? Hopefully you got that. Let me clean up the first equation a little bit. I'm gonna just multiply both sides by -1. So I get 1 over x squared equals, let's say 2 lambda over x cubed. And then the other one is 1 over y squared equals 2 lambda over y cubed. All right, who wants to guide us through here? What do you want? What do you want me to do?
I'm not sure how far I'm going to get, but I would try first starting with the setting each equation to 2 lambda equal to 2 lambda. So solve for that.
Okay, so on the first equation, how would you get 2 lambda by itself? What would you have to do?
Oh, you would just multiply each side by x cubed.
Okay, now are you allowed to do that without telling me something?
Oh, you have to say that, well, you have to say that x is not equal to 0.
If x is not equal to 0. Now, do I really need to say that? I mean, I know I do, but
But otherwise the entire thing's undefined, so.
yeah, look at the original function, right?
Mhm.
Look at f of x, y, 1 over x plus 1 over y. 0 is not in the domain, right? X equals 0 isn't even the domain of the original function. 0 for x or y. So look, technically, you don't have to say it because it's not in the original domain. And if you look back at the previous problems we did, we had to say it because, like here, 0 is in the domain of the original function. So I had to say if x, is 0 or not 0, I had to be explicit about it. Here, because it's not in the domain, I don't have to. But we'll do it just to be thorough, okay? If x is not 0 and y is not 0, which we know it's not, then you can multiply this first equation both sides by x cubed. You get x is 2 lambda. And you can do the same thing on the second equation, right? And you get y equals 2 lambda. So that's your equation 1. That's your equation 2. And I guess you did that because you want to set them equal to one another? Yeah. So that means x must be y. I like it. Once you have that, where do you want to go with that?
The third equation.
Okay, so the third equation now becomes 1 over x squared plus 1 over y squared, or sorry, y squared is now x squared, must equal 1. And that gives you 2 over x squared equals 1. And that means 2 equals x squared. And that means x equals plus or minus root 2. So we have some cases here. We have root 2 for x, and negative root 2 for x. And then the y has to be equal to x. So root 2 here and negative root 2 here. And there's also lambdas that go with these, aren't there? The lambda that goes with this first point would come from, let's see, did we ever solve for lambda? We never did. But lambda is just x over 2, right? So you just take the x coordinate, divide by 2. So root 2 over 2. And then this one right here, same thing. It would be negative root 2 over 2. Again, we don't need the lambdas, but it's not a huge deal to go find it. I think that covers that entire train of thought, doesn't it? We said if x and y aren't 0, then we got that. Do we need to consider x being 0 or y being 0? Do we need to look at that? No, because we know it's not in the domain, right? So there's that. That's it. I mean, we're done. One of these is a max, one of them's a min. So now we plug it into the function. So if I do f of root 2, That gives me the original function with just 1 over x plus 1 over y. So that's going to be 1 over root 2 plus 1 over root 2, which is 2 over root 2. And then if I do negatives there instead, I get negative 2 over root 2. So that's obviously a minimum, and that's a maximum. Questions? I think this problem was the easiest one we've done in terms of the algebra. I think the hardest thing was just that you get a little freaked out when you see all this stuff, and then you think these, partials are going to suck, but the algebra is actually not that bad. So, okay, let's look at it visually. Let's see what it looks like. So 1 over x plus 1 over y, this is the surface. Pretty cool looking surface, actually. I think it's pretty awesome. Okay, and we are restricting it to this domain right here. So this is what 1 over x squared plus 1 over y squared equals 1 looks like. And so there's the domain on the ground. And if I take just those points and plug them into the function, I get those black curves there. And I'm going to pull the surface out so we can see the black curves. The black curves are where we're trying to find the max and min of. And we found them to be, there's a highest point right there and a lowest point right there. There they are. Pretty cool. All right, how y'all feeling?
I'm starting to understand how to go through it.
Okay, good. All right, so just as you start to feel a little comfortable, right, we're now going to expand the idea of Lagrange into functions of 3 variables. See, right now we're doing everything as functions of 2 variables. We have a constraint equation, right? And the left side is a function of 2 variables equals a constant. But the beauty of Lagrange is that it extends into higher dimensions. So if you have a function of 3 variables that is subject to a constraint that involves 3 variables, then what you're going to need to do is find an x, a y, and a z, and a lambda, where the gradient of f is equal to the lambda times the gradient of g, and your constraint equation is satisfied. Which means, remember, the gradient is just the vector with the partials, right? So how many equations will we have here?
4.
4. Okay, here's what they'll be. You'll have to do the partial of f with respect to x equals lambda partial of g with respect to x. Partial of f with respect to y equals lambda partial of g with respect to y. But now we have a new element. Partial of f with respect to z equals lambda partial of g with respect to z. And then, of course, the constraint equation. That gives us 4 equations. 4 equations, 4 unknowns. Nonlinear equations can't use matrices. All right, I'm excited. Y'all ready? Y'all ready to do this? Okay, here we go. Let me take you back to last class. Get over here. Oh, whoa. I don't know what I just did. I lost all of you. There you are. Okay. So remember this problem here? Okay, we were trying to find the volume of the largest rectangular box with edges parallel to the axes that can be inscribed in this ellipsoid. So the idea here was that we came up with a formula for the volume of the box. If you look back at your notes from last class, what we determined is that the volume of that box would be 8x, y, z. Please refer to last class if you're like, where did that come from? That was the volume, and we were trying to find the maximum of it. But we have a constraint. The constraint is that point, this point right here, that point x, y, z, has to live on the ellipsoid, which means it must be constrained to that equation, right? So the x, y, and z can't just be arbitrary. It must also satisfy this equation. This is a perfect problem for Lagrange, because what we can do is we can look at this volume function as a function of three variables, x, y, and z. And then we have our constraint equation, g of x, y, z equals a constant. You see how this is like perfectly suited for Lagrange? Now, if you look back in our last class, the reason why it wasn't easy is because we didn't have this method. So we had to make the volume equation a function of a single variable. I mean, sorry, of two variables instead of three. So what we tried to do last time is we took this thing. I'm going to have to clear this. We took we found the XYZ, we found the volume equation, and we said, look, we need to replace that Z. We need to replace that Z with something with X and Y in it so we can use the methods that we had learned up to this point. So we took the equation here and we solved it for Z, and that gave us the square root, and then we had to throw it in there. And that made it a disaster when we took the partial derivatives, because we had all this chain rule, product rule, all this stuff happening. I think it's going to be a little easier today. All right. So we have this. We have a function of three variables. And remember, this represents the volume of that box, which is just 8xyz. And then we have our constraint, which I've already forgotten. 936, 436. 936, 436. There's our constraint. So this is our g of x, y, z equals a constant. So according to Lagrange, I can find the max and mins by setting up four equations. The first one is partial of f with respect to x equals lambda partial g with respect to x. Second equation, partial of f with respect to y equals lambda partial g with respect to y. Third one, partial of f with respect to z equals lambda partial g with respect to z. And the fourth and final equation is just the constraint equation, which is basically the ellipsoid. All right, so the partial of f with respect to x is just 8yz. Lambda partial of g with respect to x is just 18x. All right, second one, partial of f with respect to y is 8xz equals lambda partial of g with respect to y is 72y. Partial of f with respect to z is 8xy equals lambda partial of g with respect to z is 8z. And then our constraint. Right. Okay. Shit, right? where do you begin? It's a lot to look at, right? Dang, these are almost the same, aren't they? Those are almost the same. Could I make them all the same? I think I could, right? I could multiply the first one by x on both sides, this one by y, and this one by z. And then they would all have a left side that said x, y, z, right? But if I do that, I need to make sure that I'm saying to myself, x, y, and z can't all be 0, right? I'd have to consider that. So I'm going to do that right now. If x is not 0, y is not 0, and z is not 0, then we have that. Do I need to write these all down? I guess I will. We have that 8xy equals lambda times 18x squared. We also have that 8xyz equals lambda times 72y squared. And finally, we have that 8xyz equals lambda times 8z squared. So that's equation 1, equation 2, and equation 3, multiplied on both sides by x, y, and z respectively. And now I can start setting them equal to one another, right? So let's start with the first two. These two I can set equal to one another. So I have, I'm going to write it this way, 18 lambda x squared must equal 72 lambda y squared. Do y'all have questions? Y'all doing all right? You're okay? Gonna bring everything to one side. Go ahead. Bring everything to one side. I'm gonna factor out 18. How many times is 18 going to 72? I can't do arithmetic. Is it going evenly? Yeah, 4 times. So I can pull out an 18 lambda. Fabiola, your camera came on. Did you have a question?
Oh no, I just wanted to put it on the show that I was watching.
Oh, okay. Is this going to work? That's a difference of squares, isn't it? X squared minus 4y squared is difference of squares, so I can factor that. And now I can set all of these equal to 0. So what are my 3 results of this? This tells me what?
Lambda is 0.
Lambda 0. Okay. What does this tell you?
X is equal to negative 2y.
X had to be negative 2y. Okay. And then this last one?
X is positive 2y.
X is positive 2y. Right. So if you just set this equal to 0 and then move the 2y over, set this equal to 0, move the negative 2y over, and you get these, right?
Would you need to do a second equality where you get one for z?
Yeah, so
that you
the
can plug
question,
it back in.
yeah, the question is this enough for us to be able to figure out, because what we need to figure out is an x, a y, a z, and then a lambda, right? That's what we need to figure out. So is this enough for us to be able to get x, y, and z? Don't know at this point. But I do, before we proceed, I want to just throw something out there. I'm going to throw this away. Now, why do you think I'm throwing that away? Think back to the geometry of the problem.
We're looking for effectively a volume, and you can't have a negative volume.
Yeah, that would give you a negative volume. Remember when we drew the picture, where that point was? When we drew the picture of this right here? Do you remember this point, x, y, z? We went out on the x, then the y, and then up z. We were pretty much assuming or restricting, we were saying that the x, y, and z were all going to be in the first octant. So we are only going to be dealing with where they're all positives. Okay, and again, because the volume doesn't make sense if one single one of these is negative, right? So there's no way that x could be equal to negative 2y. Well, the only way that's true is if x and y are both 0. Then that would be true. But I already said right now that none of them are 0. So working within all of this sort of train of thought, I can throw this just because of the geometric construct of the problem. So I have a relationship between x and y. Let's try this. Let's try this. How about we do that? To do that right there, we just set those two equal to one another, didn't we? And we got a pretty good relationship here at the end. Why don't we do, I don't know. Why don't we do the first one? Why don't we do the first one set equal to this third one? Maybe we can get some there with that. So still working within the same train of thought here. I have that 18 lambda x squared must be equal to 8 lambda z squared. And then I bring everything over again. 18 lambda x squared minus 8 lambda z squared equals 0. I can factor a 2 lambda out and be left with 9x squared minus 4z squared. Another difference of squares. 3x plus 2z, 3x minus 2z equals 0. And then I'm going to get 3 results here. Either lambda is 0, 3x equals negative 2z, or 3x equals 2z. I'm chunking the middle one because again, can't be different signs. All right. I have a relationship between x and y. I have a relationship between x and z. Any ideas of where we can go with that?
Can we get one between y and z?
Say again?
Can we get one between y and z?
We could now find a relationship between y and z by setting these two equal to one another, couldn't we? But I don't know if we need to. Because I can express y in terms of x, and I can express z in terms of x. In other words, I could solve this equation here for y. And I could solve this equation here for z. So if I know that y has to be half of x and z has to be 3/2 of x, then I can go into the fourth equation now and rewrite it, can't I? Take that fourth equation. This is equation 4. And let's rewrite it by replacing our y's with half x and our z's with 3/2 x. And I'm leaving the x alone. So 9x squared, I replace the y with 1/2 x. I replace the z with 3/2 x. And look, now we have an equation with just x in it. Let's go ahead and square those. 9x squared plus 36 times, if I square that, I get 1/4 x squared plus 4 times, if I square that, I get 9/4 x squared equals 36. Just let me know if you have a question. I happen to get 9x squared plus 9x squared plus 9x squared. And I put those together, I get 27x squared. Divide by 27. That reduces, 9 goes in there 4 times, 9 goes in there 3 times, and then the square root. I'm going to throw away the negative answer. I have a solution for x. Who has questions? If I have x, I have y, right? I mean, look, y is half of x. So I know now that y must be that half of this, which is just going to take the 2 off the top. Also, I have z, because z is 3 halves times x. So if I multiply this answer by 3 halves, you should get 3 over root 3. So I think I'm there. I have x is 2 over root 3. I have y is 1 over root 3. And I have z is 3 over root 3. And lambda, you know what? I don't care about lambda right now. Lambda's whatever. Okay, this is all within one train of thought here. Okay, right? All of that was based on the fact that if x, y, and z were all not 0, then I could have done this, and my end result is to get this point. What have I still not looked at within here? What if lambda would have been 0? Right? If lambda was 0, what would happen? So in an effort to try and keep this all on one page, I'm going to do it over here. If lambda is 0, and look, I'm still working within this. Look, I'm still working within this framework that x, y, and z can't be 0. Because when I work it within that framework, I do get lambda has to be 0 or can be 0, right? So what happens if lambda is 0? Take a look back up these equations. What would this equation become? 8yz is 0, right? So you would get from equation 1, you get that 8yz has to be 0. What would equation 2 tell you? 8xz has to be 0. And this last one would tell you that 8xy would have to be 0. Well, what's the only way this first equation is true?
Y or z or 0.
If y or z is 0, right? So let's just say y was 0. If y was 0, wouldn't this one be 0 also? Right? These would both be 0. Now, what about this one? This is where things get a little weird. Look, if y is 0, then these two first equations are true, right? Now, what about this one? This would mean what? X or z has to be 0. So what if you say if y is 0 and x is 0? Then these would all be satisfied, wouldn't they? So if lambda is 0, then that forces 2 of your variables to be 0. Is that okay? Can we have 2 of our variables be 0? What's our volume going to be?
0.
0, right?
Line.
The volume is 8xyz. So if any single one of these variables is 0, we have 0 volume, which is not what we're looking for. We're looking for the maximum volume. So I think this, I'm going to say this means the volume is 0, so I'm done. Okay, I don't care about this. If any single variable is 0. And so that's why this is the only thing we have to consider, okay, is the fact that if they're all not 0, I get an answer. If any one of them is 0, I know my volume is 0. And so can I conclude that this is going to be where I have a max? Can I conclude that? Why does this have to be a max?
Can't have
If you let x or
negative.
y be 0, you get 0 volume, right? So it's like anything you compare this to, this will be bigger. We need to find the volume though, okay? The volume will be equal to, or I should say, what is the function's value at 2 over root 3, 1 over root 3, 3 over root 3. So that should be 8 times x times y times z. And that should be, let's see, if I put 2 of those roots together, root 3, I get a 3, and that cancels with that. And then on top, we get 16, and then on the bottom, root 3. There it is. All right, we have answered the question. This is definitely a max, okay? Because we know that there's other places where the volume is 0, so has to be a max. That's it. Would you agree that, I mean, there's only a few places in the entire problem where we actually take derivatives? I mean, all of this is algebra, really. The only part that requires the differentiation is right here on the gradients, setting up these 3 equations. Once you have those set up, you're good. All right, well, it's 2:33. Let's see where we are here in our notes. So if we have 3 variables, we set up these 4 equations and we can do it. Now I have 2 problems here for you to, I was going to do these in class, I don't have time. And then I have another word problem. This is a problem that you would have done in like a calculus class. Find the max volume of a rectangular box with no lid if it is to be made from 12 square meters of cardboard. Since I have 7 minutes, we can at least set this up. Do you remember that in a Cal 1 class?
Yeah, I
Remember
do.
doing something like this in Cal 1? Yeah? Okay, so we have to find the maximum volume of a rectangular box. So we have a rectangular box. It has no lid on it, right? So it's got no top to it. But it has to be made out of cardboard, 12 square meters of cardboard. All right, so let's just do what seems natural. Let's label this X, Y, and Z. What's the thing we're trying to find the max of? Volume, right? So this is going to be the volume function. It's a volume, it's a function of 3 variables, X, Y, and Z. And it simply is just X times Y times Z. That's it, right? It's just X times Y times Z. That's the volume of this box. But can X, Y, and Z be anything we want it to be? No, there's a constraint, right? The constraint is that the surface area of this box has to be made out of 12 square meters of cardboard, right? So what's the area of this box? So what's the area of this front face? What's the area of that face right there?
Length X
X times the height, which is
Z.
Z. So that's XZ. What about the back side? Same thing? XZ. So we have 2 of them. So 2 XZs plus what about the sides? That side and that side. What's that? The area.
YZ.
YZ, and we have 2 of those, right? And then we have one more thing. The bottom. What's the area of the bottom of that thing?
XY.
XY. We only have one of them because there's no top, right? And what does this area have to be equal to?
12 meters cubed.
12, right? So if I just say this is equal to 12, do you see we now have a function of 3 variables and a constraint? And off with Lagrange. You see, you don't need to do anything you did in Cal 1. You don't have to solve and get it down to a function of 1 variable. You can now do this just with Lagrange. So you now set up 4 equations, right? I'll leave that to you. I think that's going to do it for us. Are there any questions on this setup here? Function of 3 variables, constraint equation. Why don't we do this? Because the midterm grades were fluctuating. I already gave you a bonus, right, to turn in if you wanted to. Why don't we do this? I'll replace another one of your problems on the midterm, but you've got to do this problem, both of them, A and B, and this problem. It's optional, okay? But do those 2 and do that one. let's say, send it to me via email a week from today.
So these last three problems you said?
Yeah, example 7. And remember, these notes are in Canvas. If you want to go open these notes up, you can go get to them. And then example 6, which contains 2 different problems. All right, I still have 1 minute. So there's another part of Lagrange, okay? Oh, this one's a good one too. And you know what? Yeah, that's a really good problem. Find the points on the sphere. Yeah, I won't do that. That's a cool problem though. Okay, so Lagrange actually can be extended even further, where if you have a function of 3 variables, but instead of having 1 constraint, you can actually have 2 constraints, 2 constraint equations. So it'd be like, you know what, that box that we just did, that I just put up here, this, I could have like another constraint that, you know, we want to find the maximum volume, that the surface area must be 12, but let me think of another constraint. Another constraint would be something like, but the base, maybe this length has to always be 3, y always has to be 3 times x. So maybe I give you one more constraint, that this always has to be 3 times longer than this. That'd be another constraint I could give you. And so you would have another equation, constraint equation, which you would move everything to one side and make it equal to 0. So you'd have a second constraint. If you have, go ahead.
Wouldn't it need to be with 3 variables though?
There is, it's this is 0z. You can't see it. It's 0z plus.
Oh, okay.
Yeah, so it's not there. See, I could have said, you know, the other constraint is that when you add all these sides up, like this length plus that length, it has to be 5 or something like that. So then you would say x plus y plus z is 5. The constraint can be anything that relates the variables together, even if it only contains 2 of them. So Lagrange says, you know what, we can handle that. Okay, Lagrange says if you have 2 constraint equations, then you're still going to have 4 equations, but you're going to have 5 equations this time, but what you'll have is the gradient of f has to be lambda times the gradient of g, which means it has to be a scalar multiple of this gradient vector plus another scalar, mu, times the gradient of h, which is the other constraint. Now, I'm not going to test you on this. I'm not going to give you any problems like this, but I just want you to know that there are ways to extend out Lagrange into more complicated scenarios. So that means you'd have 3 equations, 2 constraints, you have 5 equations here. All right, and then, you know, at some point in my life when I was doing these notes, I actually wrote programs to do Lagrange method. So I wrote a program that actually, you just put in the function, like let's just do the one that we just did. Oh, hold on, where is it? We did this one. Didn't we do 8 times x times y? Or you know what, let's do the one that no, I don't want to do that one. 8 times x times y times z. That was the volume thing, and we had to be constrained to that. You know, I'm not going to do it. Never mind. It's acting weird. The point is that if you are a computer person and you know how to program, then you can actually just write code to do this stuff. So you don't actually have to go through the actual process of. So here's the code there, and it'll actually go and find the x, y, z, and lambda.
I think it didn't work because of the dynamic updating.
Yeah, I hadn't hit that button up there, so it messed things up. But all right, that is it. We are done. Is that it for the week? Is today Wednesday? Wow. All right, it is what it is. I'm trying to keep us on schedule. It's, you know, it's really hard. We're right here. We're officially a week behind. We're gonna do our best, but maybe I can make up some ground next week here. I've been thinking about the final. I know it's time to go, but I'm thinking about the final. And I think what I'm gonna do for the final is I'm gonna give you a list of problems, a rather lengthy list of problems, because our final is gonna cover just a tremendous amount of material, right? I mean, it's gonna be a lot on the final. So I'm gonna give you a list of problems. I don't know how long that list of problems is gonna be. And you're not gonna turn it in for a grade or anything like that. When you come to the final, I'm going to pick certain problems off that list. Like off that list, which means that's going to force you to do them all and know how to do them, right? And then when you get to the final, you just have to be able to reproduce that. But you will have to maybe do 8 problems out of a list of maybe 25 that I give you. So that way you have something to study. But see, it's going to be impossible on the final for me to give you a test that you can finish in the time that covers all the material that we need to cover on that test. So to be fair, I'll give you the problems from the test basically, and you just need to know how to do them all. I hope that makes sense, and I hope that seems like it'll be a fair way of doing it, because it could be really shitty if I give you a final and you're like, man, you know, all those problems, I didn't even study those problems, you know, like, because there was so much to study and I should have focused on this. And this way, no surprises, right? But you need to have done it all. All right. Have a good weekend, everyone. Do your homework, do as much as you can through Lagrange multipliers.
Thank you.
All right, have a nice
Professor.
weekend.
Thank you,
Take
sir.
care. I'll hang out for a minute if you have a question.